Hello, everybody. I'm inviting you to continue a journey to the center of the Earth. If you haven't watched part one, please do. We are continuing the journey. We are at the border of lithosphere and asthenosphere, and we are going deeper and deeper. Asthenosphere, if you remember, is the mechanical layer, is a soft plastic mechanical layer. Compositional is a mantle, but if you remember from part one, the compositional layer mantle covers much more. So we created upper mantle and we borrowed, borrowed some part of this called uppermost upper mantle that stick to crust and create a lithosphere. So in this case, asthenosphere is relevant to upper mantle, but the upper mantle sticks to the crust, and together they create lithosphere. Asthenosphere or upper mantle has a density up to 4 grams per cubic centimeters. So comparing to lithosphere, it's denser. And asthenosphere is a weak layer that readily deforms by creep. There is also a so-called low velocity zone, 50 to 100 kilometers thick at the top of asthenosphere. And there are three main discontinuities that we will talk about there. The low velocity zone is a widespread, partially molten layer within the asthenosphere. As I told you, it's at the top of the asthenosphere, so close to lithosphere. It's a low viscosity layer, and there are gradual changes in pressure and temperature with depth. Traveling deeper, we can observe a mantle transition zone. It's a zone associated with the phase transformation of minerals under the influence of high pressure and temperature. So until now, the olivine is the dominant mineral. It's a greenish one, usually occurs in two forms, forsterite and feuerite. And 410 kilometers discontinuity is a border when olivine changes into wachsleite. It's also wachsleite is also called like beta phase of olivine. Going deeper at a depth of 520 kilometers, wachsleite changes into ringodite. Ringodite is called the gamma phase of olivine. Also, at 560 kilometers, there is discontinuity when calcium garnet changes into calcium perovskite. It's not so bold comparing to the discontinuity above and beneath it, but it's distinguishable. And at the depth of 660 kilometers, ringwoodite changes into bridgmanite, also known as perovskite. It's a border of the upper and lower mantle of, if we upper names of the layers in mechanical sense, there is the border between asthenosphere and mesosphere. On this graph, we have a comparison between pressure, temperature, and depth, and changes between olivine, wachsleite, ringwoodite, and bridgmanite. Going deeper, we are at mesosphere or lower mantle. If you remember, mechanical layer is a mesosphere, still plastic layer compositionally is a silicate mantle. And if you compare both the layers, we got lower mantle, so this is a stiff plastic rocky layer. And the density is again higher comparing to asthenosphere. There was up to 4 gram per cubic centimeters. Now there is up to 5.6 gram per cubic centimeters. In the mesosphere, the double prime layer is distinguished. Core mantle boundary layer is so-called discontinuity, Gutenberg discontinuity, is the most important border in the Earth interior. We talk about it in the first part one of this video, is the border between silicate layers and metallic layers. The double prime layer is a layer up to 250 kilometers above core mantle boundary. So first, why this name, D double prime? It's a little bit different that we talk mesosphere, lower mantle, or something like that. So this name is taken from Keith Bullen. He distinguished 6 layers, and mantle was described by letter D. Later it was divided in D prime layer and just D double prime layer. So that's why this name. The double prime layer is characterized by steep temperature gradient. If you remember this graph from part 1, there is a very bold steep temperature gradient. There is also transition perovskite, Bridgmanite, to post-perovskite at around 125 gigapascals. And there is notice the global occurrence of the changes of post-perovskite to post-perovskites that destabilizes the thermal boundary and enhances plum upwelling. There is also a graveyard of subducted slabs, and there is a base of large low shear velocity provinces and ultra-low velocity zone. So if you look at the graph at my right, you can see there is a really busy layer. So talking about large low shear velocity provinces, there are 2 of them beneath Pacific and Africa. They are also called Jason and Tuzo provinces. They are thousands of kilometers wide and around 1,800 kilometers high. So from the border at the depth of 2,900 kilometers, they reach the depth around 1,100 kilometers. There's a theory they are composed of a bundle of thermochemical upwellings enriched in denser material, and compositionally they are divided in 2 domains, a primordial bottom domain and a shallow domain, producing different types of plumes to rise from the flanks and roofs. There's a wonderful cartoon presenting the large low shear velocity provinces. And the study of large-scale heterogeneity within SVPS has important implication for understanding of the evolution and composition of the mantle. Large low shear velocity provinces are connected with occurrence of hotspots. The hotspots are located on the top of the provinces and along the margins, what is represented on this this figure, and this is also visible on the very nice cartoon. Uh, the provinces are also connected with ancient large igneous provinces. Large igneous provinces is lava flat or traps, and location of ancient large igneous provinces related to the present day LLVAPS margins inform us that they are stable in a long time. Ultra low velocity zones, they are tiny patches on the core mantle boundary, reduces S waves and P waves. We talk about seismic waves in part two, so please watch part one. Reduces S waves and P waves, respectively 30 and 10%. They are small, 10 to 40 kilometers high and hundreds of kilometers laterally. And the example of that is, for example, Hawaiian plume. There are many theories of origin of ultra-low velocity zones. There are thermal, compositional, or primordial. Primordial, the recent study suggests that variation in the Earth's core mantle boundary might come from a water-rich magma ocean at the very beginning of Earth existence. And when this magma ocean solidifies, it creates a unique oxidized mineral that is different from the surrounding mantle. And this mineral has a strong attraction to iron, which helps it to stay stable on the border, forming areas with low seismic velocity and high electrical conductivity. These low seismic velocity areas might be due to iron-rich minerals from the solidified wet magma ocean. Compositional theory can notice that the subducted oceanic crust is partially molten due to chemical differences and temperature perturbation near the core mantle boundary. And then the partially molten materials could be pushed the mantle flow on the edges of the large low shear velocity provinces. If we compare asthenosphere and mesosphere, we notice that asthenosphere or upper mantle is responsible for volcanism in subducted zones. Mesosphere is responsible for hotspots. For example, Hawaiian Islands. And we are going deeper and deeper. Outer core, so mechanically is a liquid outer core. Compositionally is only a core. If we compare both layers, we got outer core. There is a liquid alloy of iron and nickel and some other elements, and outer core does not transmit S waves. That's why we know that it's liquid, because S waves do not travel through liquid medium. And comparing density, a lower mantle density was up to 5.6 gram per cubic centimeters. Outer core 10 to 12.7 gram per cubic centimeters. So it's at least 2 times more. In outer core, there are distinguished layers, E prime layer, F layer, and outer core is also responsible for magnetic field. E prime layer is topmost outer core layer, 100 kilometers or so thick. It's created by deep transport of water to the core mantle boundary by subducted slabs, and it's represented on this figure. And the exchange of hydrogen and silicon between lower mantle and outer core takes place in this layer. So in this case, E prime layer is high rich and silicon deficient layer is it's characterized by a lower density and a lower velocity. Recreating conditions of high pressure and high temperature that are relevant to the outer core topmost layer. So around 3,700 Kelvin and 137 gigapascal allowed us to estimate what can happen in E prime layer. So that's why we can think that there is a high rich and high reaching means hydrogen rich and silicon deficient layer with lower density and lower velocity. The next distinguished layer in outer core lies on the inner core boundary. It's around 150 to 400 kilometers thick layers, characterizing by slowing down P waves. It's a slurry layer. Recent studies suggest that there is a slurry mixture of liquid and solid material below the liquidus temperature of iron and lighter elements. Liquidus temperature is a specific temperature above which a material is liquid, but it's a maximum temperature at which crystal coexists with the melt form in a thermodynamic equilibrium. The slurry layer is characterized by crystallization of iron throughout the entire F layer. Light elements remain in the liquid. Actually, oxygen is expelled to the liquid. Silicon and sulfur evenly portioned between liquid and solid. Heavy elements sink to the bottom of inner core boundary and causes transport of light elements toward core slurry boundary. So the boundary of F layer, top boundary of F layer. And it's characterized by stable density stratification. Now you can ask me, why are shear waves not transmitted by the solid fraction? So the answer is simpler than simple. The fraction solid is small, is too small to be detected by seismic observation. Why F layer is so important? The freezing of the solid inner core releases light elements into the liquid outer core, drives compositional convection, and the compositional convection is a power source for the present geodynamo. Today, 80% of the convection in outer core is a compositional one. Due to heat extraction on CMB, there is still thermal convection estimated for 20%. Historically, in the Earth history, the thermal convection was more significant. But how does a geodynamo work? So Simplifying, kinetic energy is transferred to electric current in a conductive medium, and the current produces magnetic field and magnetosphere. And please remember that there is nothing about ferromagnetism because Curie point for iron is 770 Celsius. And so the temperature in outer core is higher. And the CMB is estimated between 3500 and 42, and on the inner core boundary between 4500 and 5500 degrees. What does happen in the outer core? So convective fluid is in a large volume in the outer core, and it's perturbated by a solid body, by the inner core. You can imagine the outer core as a bigger sphere, and inside you have a inner core. That produces convection currents. And rotation. Coriolis force tends to organize fluid motion into columns aligned with the Earth's rotation axis. And electrically conducting fluid moves helically with high velocity, produces electric current. And the electric current produces magnetic field. Geometrically large circuit causes that decay time of electric current is large. So that's why dynamo effect does not extinguish. So it's a self-sustaining cycle that gives us the wonderful magnetic sphere. The magnetic field produces magnetosphere that is deflects the most harmful solar light, and it's a key factor for life on our planet. The magnetosphere is a barrier for solar wind, but some particles are trapped by the atmosphere. Then we can see aurora borealis, but also the trapped particles causes many disturbances, especially for electronic devices. And now we are in the inner core. Mechanically, the inner core is a solid. Compositional layer is only one, it's core, and comparing both, we got inner core, metallic solid inner core near melting point. The density is higher than 12.8 gram per cubic centimeters, and inner core radius is about 1200 kilometers. And recent studies show innermost inner core with radius about 650 kilometers. So we just talked about crystallization in F layers. The crystallization means that the inner core grows. It grows around 1 millimeter per year. The inner core is solid, but please do not think about the inner core as a cannonball. The inner core surface is slowly changing shape over time due to influence of the outer core. There is a 4 to 8 kilometer thick mushy layer between the inner core and the outer core. The inner core also shows west anisotropy due to crystallization rate, and inner core rotated faster and then slower than the rest of the Earth in the last few decades. And there is something inside the inner core that's characterized by seismically different region, high Q, characterized by high Q. Q is a quality factor used to describe seismic attenuation. Q increases when the density and the velocity increases. But what's this? What is the region? Seismic observation revealed radial variation in wave speed and anisotropy, and it's so-called innermost inner core with radius about 650 kilometers, and probably the innermost inner core records early phase of the inner core evolution. So now we are in the center of the Earth and we need to come back to the surface. And we will do it by summarizing each layer from the center to the surface. So we are in the innermost inner core, so in the metallic part of the Earth. The whole inner core is solid, mainly made with iron, and there is a distinguished layer of innermost inner core. The pressure is enormous, up to 360 gigapascals. Outer layer. So you remember we talked about slurry F layer. The outer core is liquid, made with iron mostly. It's responsible for geodynamo. We talk about E prime layer at the top of the outer core, and the pressure is between 135 to 330 gigapascals. So it's pretty high, right? And now we are crossing the most important border in the whole Earth interior. It's the border between outer core and lower mantle. It's the border between metallic inner part and rocky outside part of the Earth interior. So lower mantle, we talked about the double prime layer, where is the change between this transformation from perovskite to post-perovskite. There is a lithosphere slab graveyard. There is sources of hotspots. There is the base of large low shear velocity provinces and ultra low velocity zone. The whole layer is a stiff plastic, and bridgemanite is a dominating mineral. The pressure is around 24 up to 135 gigapascals. And now we are crossing rapid discontinuity. So we are going from lower mantle to upper mantle, and it's a soft plastic layer. It's relevant to asthenosphere. And in this layer, there is a transition if we are going from the interior. So it's a transition between ringwoodite to wurtzleite and wurtzleite to olivine. And pressure is lower and lower, and the border with lithosphere, there is around 10 gigapascals or even less. And we crossed the border between asthenosphere and lithosphere, and we even crossed Moho discontinuity, so the border between crust and uppermost upper mantle. We are in the rigid layer responsible for tectonic plates, and the pressure is lower and lower from around 10 gigapascal to the not to the zero, around 10,000 hectopascals on the surface. So we are on the surface, and thank you for joining me on this journey to the center of the Earth and back. And there is a list of selected references that can be useful also for you. So thank you for watching this video. If you like it, please give me a thumb up and please subscribe. Both actions help me a lot. With geo greetings, see you in the next video.